rectangular bar, apply force, P, length is L, cross-sectional area is A, meters squared, length is in meters or millimeters, force is in newtons. Assume material is homogeneous and isotropic. That means the property is uniform throughout the sample and also isotropic, that is not directional dependent. That means the properties along x, y, and z would be same, independent of direction. Hooke's law applies. That's to say deformation is elastic, stress is proportional to strain, constant of proportionality is Young's modulus. And stress is in unit pascals, strain no units, so stress would be, Young's modulus would be in pascals. But often, stress is quoted in megapascals, modulus is quoted in gigapascals. The reason is because strains are too small, like 10 to the minus 3 or so, for metals in the elastic region. So when you divide stress with a very small number, Young's modulus would be gigapascals. Megapascal times 10 to the 3 or 10 to the 2 would push the modulus into gigapascal region. Stress, simply Young's modulus times strain, where stress is force divided by area and strain is change in length divided by origin of length. Free writing P over A times change in length divided by L. Rearranging that equation, delta L is equal to PL over AE. We often call this uniaxial extension in elastic range. Force is in newtons, length is in millimeters, and area is in millimeters squared. Young's modulus you have to write in Newton per millimeter squared or megapascals. When we apply force P, there will be an extension along Z, but it will cause contraction along X and Y, lateral dimensions. So this will lead to the definition of Poisson's ratio, which relates the lateral strain to axial strain, minus lateral strain divided by axial strain. What are the lateral strains? Minus epsilon x divided by axial strain epsilon z. That is equal to minus epsilon y divided by epsilon z, lateral axial. Because of isotropy, epsilon x is equal to epsilon y. The strains are same in x and y directions. They are minus nu epsilon z. Epsilon x is equal to epsilon y is equal to nu epsilon z. Hooke's law applies elastic. So sigma is equal to Young's modulus times strain. So strain then is equal to sigma divided by E. Substituting that here, epsilon x is equal to epsilon y is equal to minus nu sigma divided by E. We can also write, if you like, sigma z, because the stretch is along z direction, sigma z over E. Further expand that, minus nu, sigma is force divided by area. Notice the similarity of this equation. Previously, PL over AE. We haven't finished yet. So let's isolate epsilon x is change in Lx divided by Lx. Change in x dimension divided by original x dimension. Similarly, epsilon y is change in y dimension divided by original y dimension. Change in Lx then is equal to change in y dimension. Now notice the similarity of this equation to delta L z is PL over AE. Now notice this is a stretch in that direction, so no Poisson ratio, but accompanied by contractions along x and y. So Poisson ratio determines the contractions for a given axial loading. Also, I must mention here in the formula, we say minus lateral strain divided by axial strain. Why negative? Because lateral strain, as I said, is contraction. That is a negative strain. Because it's contraction, this is a negative strain. So negative, negative makes positive. So we get a positive Poisson ratio by you putting a negative here. Poisson ratio varies between 0.5 and 0. That's the maximum value. The material is incompressible. So for Poisson ratio 0.5, material is incompressible. The modulus of compression becomes infinity, or volumetric strain goes to 0. There's no volume change. It's incompressible. For Poisson ratio, as it approaches 0, the material is very compressible. The volume changes when you apply the stress. Rubber has a Poisson ratio is approximately 0.5. Rubber is an incompressible material. It will resist volume change. Core Poisson ratio around 0, so it will accommodate volume change. For metals, Poisson ratio is approximately 0.3 for most metals in that range. If we have a solid cylindrical bar, length L, force P, cross-sectional area is A, and the diameter is D. So in this case, solid cylindrical bar. When you apply the same principle, Poisson ratio is minus lateral strain divided by axial strain. Now, what is lateral strain? Change in diameter divided by original diameter. What is axial strain? Change in length divided by original length. If you're dealing with change in diameter, the original diameter, change in length, original length, so you can use this form of the equation. Poisson ratio is also equal to, again, minus change in diameter divided by original diameter. Axial strain, you can write it as epsilon z, which is equal to, by Hooke's law, sigma z divided by E. Okay, so minus delta D over D divided by sigma over E. So if you have been given the stress and the Young's modulus, you can use that form. If you've been given stretch and original length, you can use that. Depends on where the question is taking you, which form of the equation you want to use. Basically, they are the same. Or you can use mu is equal to minus delta D over original length D divided sigma is force divided by area. Or you can use that form. If you have been given force and cross-sectional area modulus, you can use that. Or Poisson ratio may be given, you may be asked to find the dimensions, or you may be asked to find the force to create those changes in the dimensions for a given Poisson ratio. These are the different kind of formulations of the same thing for a circular cross-section. We initially dealt with rectangular cross-section, and now we use the circular cross-section.